Good day, Dr. Nas. My name is Michael Umako, the graduate student in the School of Computer Science at Western Illinois University. Today, I'll be giving a short presentation to review a selected article titled Protecting Cloud Virtual Machines from Commodity Hypervisors and Host Operating System Exploits by S. Lee, J.S. Core, and J. Neal. Um, in fulfillment of the project requirements for CS513 topics in operating system for summer 2024 session. This presentation is divided into the following sections. Firstly, I'll start off with a brief overview of the article in the abstract, then an introduction to the current state of commercial hypervisors currently in use. I'll also talk about assumptions made by the authors in the testing environment to serve as experimentation limits used for their research and the threat model used for their investigation. This will be followed by a brief on the hypervisor design created by the authors to solve the security issues. Implementation of the design follows, after which the security analysis showcasing the properties of the hypervisor architecture. Uh, this will be followed by the results of their experiments, after which the presentation will be concluded with a summary of important findings by the authors. At the very end, a select few articles and papers relating to the research are also shown as references. As we are well aware that hypervisors are widely used by many cloud computing companies uh, or providers to host virtual machines for businesses or even individuals that need their workloads hosted offsite. This brings about many security risks relating to assuring the confidentiality and integrity of information, as these hypervisors in use by cloud providers have very large code bases that contain a lot of vulnerabilities. Um, so even with these vulnerabilities that are present on these hypervisors that the cloud providers use, the relatively cheaper cost of running compute and storage workloads is one of the major reasons that uh, businesses and users usually decide to move their information, data, and their compute requirements to virtual machines that are offsite. Um, mostly, most of these are cloud providers that use commercial hypervisors to host their VMs running in the cloud. These hypervisors have full control over the physical hardware, and they provide virtual machine abstraction, which oftentimes are integrated with a host operating system kernel to leverage the kernel functionality. Um, like mentioned in the article, it is mentioned in the article that KVM is integrated with Linux and Hyper-V is integrated with Windows. This results in large potential attack surface with access to VM data in CPU registers, memory, and even boot images. As a result, attackers that successfully exploit hypervisor vulnerabilities, they can gain access to virtual machine data, which is obviously not what the cloud providers or users want. So recent trends in hardware virtualization support have provided an opportunity for hypervisor design to address this security problem. Many applications are now using end-to-end encryption for input channels, secure network connections, and disk encryption. This somewhat reduces the need for hypervisors to secure uh, input and output channels, since applications can do a better job of providing end-to-end input and output security solutions. So based on this, the authors created HypeSec, which is a new hypervisor design for retrofitting commodity hypervisors used by cloud providers to massively reduce the code base or the code size of the trusted computing base. So this new design provides strong security for VMs running unmodified guests while also causing slight performance overhead for application workloads. This design employs microkernel principles, which involves just applying a little bit of restructuring to the existing hypervisor with slight modifications, all the while maintaining full functionality of the hypervisors. So um, this new hypervisor design called HypeSec divides the hypervisor into a small trusted core called the core visor and a large untrusted host called the host visor. So more on this design, I will discuss more on this design later in the presentation. So in testing this new hypervisor design, the authors made a couple of assumptions that serve as restrictions or boundaries for their tests. These restrictions are that they assume that the VMs use end-to-end encryption channels to protect their input and output data. They assume that hardware virtualization supports and inputs and outputs memory management units similar to what is available on x86 and ARM servers. They assume that the hardware security module is bug or vulnerability free and trustworthy. They also assume that HypeSec trusted computing base and the core visors do not have any vulnerabilities and that they can be trusted. Lastly, they assume that it is computationally infeasible to perform brute force attacks on encrypted um, virtual machine data, and any encrypted communication protocols are assumed to be designed to defend against replay attacks. So for the threat model, the authors consider the following scenario. Firstly, that an attacker would have only remote access to the hypervisor and to its virtual machines, including administrators without physical access to the machines. Um, the attacker's goal is to compromise the confidentiality and integrity of VM data, which includes VM boot image containing the guest kernel library, data residing in memory addresses belonging to the guests, um, guest memories copied to hardware buffers, uh, data on VM disks or file systems, data stored in VM CPU registers. The model also considers that the remote attacker does not have physical access to the hardware, so that the following attacks are out of scope. Physical tampering of the hardware is not part of the threat model. Um, Physical tampering of the physical memory, because these threats are better handled with on-site security and tamper-resistant hardware. Cloud providers like Google, they go through very, very great lengths to ensure that physical security of their data centers and restricts physical access to even some of their administrators. Um, the authors also assume that VMs do not voluntarily expose its own data, whether on purpose or by accident. They also assume that the attackers may try to attack other VMs on the host from a compromised VM from which uh, the HypeSec provides protection. So next, I'm going to be talking about the hypervisor design. HypeSec reduces the trusted computing base necessary to protect VM confidentiality and integrity while retaining full hypervisor functionality. So it was observed by the authors that many HypeSec functions could be supported without access to the VM data, like virtual machine CPU register data, which is unnecessary for CPU scheduling. So this new hypervisor design, HypeSec, it uses microkernel design principles to divide the current or usual commodity hypervisors into two parts. Firstly, a privileged and trusted co-visor, which has full access to VM data. Then a deprivileged and untrusted host visor that is responsible for most hypervisor functionalities. Unlike previous microkernel approaches, HypeSec is designed to restructure existing hypervisors with little modifications, as opposed to requiring a total clean slate redesign. Dividing the hypervisor like this results in significantly smaller trusted computing base that is still flexible enough to allow modern hypervisor features like device emulation, virtual machine management, virtual CPU scheduling. Uh, the core visor is kept small by only performing VM data access controls and hypervisor functions that need full access to VM data, like virtual machine boots, CPU virtualization, and page table management. And it also runs in hypervisor execution level 2. Um, the untrusted host visor handles other complex functions that don't need access to VM data, including resource management, such as CPU scheduling, memory allocation, and it runs in the less privileged kernel execution level 1 mode. The core visor has its own memory and uses nested page tables, that is NPTs, to ensure memory isolation between the host visor and the VM itself. As a result, a compromised host visor or virtual machine cannot control hardware virtualization mechanisms or access core visor memory, and hence cannot disable HypeSec. Next, I'll talk about some of the features in the new HypeSec design. In implementing the new hypervisor design, HypeSec requires a higher privilege CPU mode, nested page tables for memory virtualization, and an input-output memory management unit for direct memory access protection. HypeSec's core visor is initialized at machine boot up and runs in execution level 2 to fully control the hardware. HypeSec's code is embedded in the Linux kernel library, which is verified and loaded via the Unified Extensible Firmware Interface. The host visor allocates resources and configures the hardware for the core visor. The host visor then makes a hypercall to the core visor in execution level 2 to enable HypeSec. The HypeSec's ARM implementation leverages KVM stroke ARM that is split into and an execution level 2 low visor and an execution level 1 high visor to support ARM virtualization architectures. This is done because execution level 2 is necessary for controlling hardware virtualization features, but Linux and KVM are designed to run in kernel mode execution level 1. Uh, so as a result, the low visor manages hardware visualization features and VM hypervisor switching, while the high visor contains the rest of the hypervisor and Linux. Um, However, the low visor cannot protect VM data if any other part of Linux or KVM are compromised. HypeSec also supports secure VM boots using ARM Trust Zone based on the Trusted Execution Environment Framework to store the signatures and keys securely. HypeSec takes QEMU to load the VM boot images to VM memory, but the core visor requires a QEMU to take part in its verified boot process. The core visor retrieves the VM boot image signatures and the user public key from the trust zone for verifying the VM images that are remapped to the address space. Uh, HypeSec's hardware requirements can also be satisfied on Intel x86 architecture by using virtual machine extensions and the input-output memory management units. Existing x86 hypervisors can be retrofitted to run the core visor in virtual machine extensions, root operations, which allows control of virtualization features for reducing the privileges of the hypervisor. The host visor runs in virtual machine extension root operation to provide resource management and virtual inputs to outputs. Next, I'll talk about 5 properties of HyperSec architecture and also how their combination provides an additional set of security properties regarding HyperSec's ability to protect the integrity and confidentiality of virtual machine data. So for the five properties of HypeSec, HypeSec's core visor is trusted during the system lifetime against remote attackers. That is, HypeSec leverages hardware secure boots to ensure only the signed and trusted HypeSec binary can be booted. Just like I mentioned before, this prevents an attacker from trying to boot or reboot the system or to force it to load a malicious core visor. The second property, which is based on property one, is the trusted core visor verifies the signatures of the VM images loaded to VM memory before they are booted. The public keys and signatures are stored using trusted execution environment APIs for persistent secure storage. A compromised host visor therefore cannot replace a verified virtual machine with a malicious virtual machine. Uh, the third property, also based on property one, HypeSec prevents the host visor and a given VM from accessing memory owned by other virtual machines. The core visor, it tracks ownership of physical pages and enforces uh, inter-VM memory isolation using nested paging hardware. A compromised host visor could control a direct memory access capable device to attempt to access virtual machine memory or compromise the core visor itself. However, the core visor controls the input-output memory management unit and its page table. So the host visor cannot access a core visor or virtual machine memory via direct memory access. For the fourth property, HypeSec protects virtual machine CPU registers by only granting trusted core visor full access to them. The host visor cannot access VM registers without permission. Attackers cannot compromise virtual machine execution flows since only the core visor can update the VM registers. The fifth property, HypeSec protects the confidentiality of a given VM's input/output data against the host visor and all other VMs, assuming the VMs employ an end-to-end approach to secure input/output. This is based on properties 3 and properties 4. IPsec protects any input/output encryption keys loaded to the virtual machine CPU registers or memory. So a compromised host visor cannot steal these keys to decrypt or encrypt input or output data. This same protection holds for other VMs as well. So four additional security properties of IPsec architecture that were derived from the first five are as follows. Um, Using the reasoning in the fifth property with the additional assumption that inputs or outputs can be verified before it permanently modifies input or output data. HypeSec also protects the integrity of virtual machine input or output data as any tampered data will be detected and can be discarded. The seventh property, which is assuming a VM takes an end-to-end approach for securing its inputs or outputs. HypeSec protects the confidentiality of all the VM's data against a remote attacker, including if the attacker compromises any other virtual machines or the host visor itself. It's based on the first, the third, and the fourth property, which means that a remote attacker cannot compromise the core visor, and any compromise of the host visor or any or another virtual machine cannot allow the attacker to access virtual machine data stored in CPU registers or memory. This, combined with the fifth property, allows IPsec to ensure the confidentiality of all the virtual machine data. The eighth property, which is assuming a VM takes an end-to-end approach for securing its I/O and that the inputs or outputs can be verified before it permanently modifies any VM data. HypeSec protects the integrity of all the VM data against a remote attacker, including if the attacker compromises any other virtual machine or the host visor itself. It's based on first, third, and fourth party as well, which means that it ensures that a remote attacker cannot compromise the core visor and that any compromise of the host visor or any other virtual machine cannot allow the attacker to access VM data stored in CPU registers or memory. thereby preserving the virtual machine CPU and memory data integrity. This combined with property 6 allows HypeSec to ensure that integrity of all to ensure the integrity of all the VM's data. So for the ninth property, if both the host visor and core visor are not compromised, and the host visor is responsible for handling input or output, then the confidentiality and integrity of VM's input or output data will be protected against other VMs. So this property combined with the third and fourth properties allows HypeSec to ensure confidentiality and integrity of all VM data. This guarantee, the authors state in their paper that is equivalent to what is provided by traditional commodity hypervisors like KVM. So the next slide talks about the experimental results that were carried out by the authors. All the experiments the authors performed, they were ran on ARM server hardware with virtual environment support. But the hardware did not support ARM virtual host extensions. So for client server experiments, the clients ran on x86 machines with 24 Intel Xeon CPUs, having 96 gigabytes of RAM, over 10 gigabytes unsaturated network connections. Um, this specific slide, it shows two tables uh, having tests performed to measure the costs of low-level hypervisor operations using the new HypeSec design and the results. The authors used the KVM unit test framework as shown in the micro benchmarks table on the uh, as shown in the micro benchmark table on the left to measure the cost of transitioning between a virtual machine and the hypervisor, initiating a VM to hypervisor operating system kernel requests, emulating user space inputs or outputs with QEMU. This test was slightly modified These tests were slightly modified to measure the cost of virtual IPIs and to obtain cycle counts on ARM to ensure detailed results by configuring the VM with direct access to cycle counter. The micro benchmarks table measurements on the right show that the results of both the standard KVM hypervisor and HypeSec. An analysis of these results show that HypeSec introduced approximately 5 to 15 or 19% overhead over KVM. HypeSec did not increase the number of traps in the operations that were measured. The kernel input outputs, the user input outputs, and the virtual IPI measurement show that relatively higher overhead than HyperCore on HypeSec because of the costs involved in securing data transfer between VM and host visor for input stroke outputs interrupt virtualizations. So this slide shows real application workloads that were run to evaluate HypeSec compared to standard KVM. These workloads are like a mix of widely used CPU and input-outputs intensive benchmarks, as seen on the application benchmarks table to the left. The application benchmarks performance table to the right shows the relative overhead of executing in a VM in our Autos 4 VM configurations compared to executing natively on KVM. Uh, the four configurations as shown at the top of the table on the right. The four configurations are uh, unmodified KVM and guests kernel without full encryption, without full disk encryption, KVM with full disk encryption, HypeSec and paravirtualized guest kernel without full disk encryption, and lastly, HypeSec with full disk encryption. So lower numbers mean less overhead, and the performance table show modest overhead overall for HypeSec compared to standard KVM. As you can see, the overhead increase for HypeSec in many cases is less than 10% with full disk encryption enabled. This slide talks about the how the authors evaluated the effectiveness of IPSec against compromised host visors by analyzing the common vulnerabilities and exposures, that is the CVEs, and identifying the cases where IPSec protects VM data despite any compromise, assuming an equivalent implementation of IPSec for x86 platforms. So the CVEs are related to Linux or KVM were analyzed in two separate cases. For this slide, this first case is a malicious VM that exploits KVM functions supported by Hypervisor as shown in the table. So among these lists of the selected CVEs, 16 were x86 specific and one is specific to ARM, while the rest were not dependent on architecture. So the second case that was analyzed is where an unprivileged host user that exploits vulnerabilities in Linux are seen in the table. With the same tests that were performed previously in the previous slide, the attacker's goal in both cases would be to exploit these CVEs to obtain the hypervisor privileges and compromise the virtual machine data. So as seen in the table, the CVEs related to uh, this paper's threat model consists of could result in information leakage, privilege escalation, remote code execution, memory corruption in Linux. So while a KVM does not protect VM data against any of these, while it does not protect VM data against any of these, HypeSec protects against all of them. HypeSec protects against all of them. So HiveSec does not guarantee availability and cannot protect against CVs that allow VMs or host users to cause denial of service in the host visor. So vulnerabilities that allow unprivileged guest users to attack their own VMs, like this CV 2014, previous slide, like CV 2014 784 and 2018 1087 are unrelated to HypeSec threat model. So the author states that this will be addressed in future research. So in conclusion, HypeSec, which is a new approach to hypervisor design, uh, reduces the code size or the trusted computing base required for protecting virtual machines. So this new design uh, divides current commodity hypervisors into a small trusted core visor and an untrusted host visor, with the host visor containing the vast majority of hypervisor functions, including the entire host operating system kernel. The core visor leverages hardware virtualization support to execute at a higher privilege level and provides access control mechanisms to restrict host visor access to VM data. So it can be simple because it only needs to perform basic CPU and memory virtualization. When VMs use secure input or output channels, IPsec can protect the confidentiality and integrity of all VM data. The authors were also able to demonstrate with their experiments that HypeSec could support existing commodity advisors by retrofitting KVM ARM with the resulting trusted computing base, many orders of magnitude less than the original KVM stroke ARM. So at the end, we can arrive at the conclusion that HypeSec provides strong security guarantees to virtual machines with just little performance overhead increase for application workloads. So this next slide does contain a few select references from the paper. The paper has over 96 references, uh, but I just selected some that were of vital importance to the presentation. This brings me to the end of the presentation. Thank you very much.